This is video 54 in our series Electrical Circuit Analysis. The playlist for all our videos is found at the website digital-university.org. If you watched our previous video, we spent a little bit of time discussing inductance and Lenz's law and counter voltages that are induced across a coil. And just to briefly recap, we stated that if we have just a simple circuit like this, and this is a constant voltage source, then say at time t equals 0, we close the switch here. And then we take just an instant of time immediately after that. And what we said in the last video is that you will find that there is an induced voltage across this coil, and at this instant in time, that induced voltage will equal E at that instant in time. Now, the expression for the voltage across the coil is its inductance times the rate of change of the current, and its polarity is such that it opposes the flow of the current into the coil. That was just Lenz's law. Now, the voltage across the coil, this induced voltage, and we're writing it with circles around it because this is not a voltage drop now. This is an induced voltage that occurs. It doesn't stay at this value. It looks like this. Time. This is the voltage across the coil. It'll start off being equal to E, our battery, and it falls off like this. But the reason why it can exist even to begin with is that when we close the switch, you can imagine just a small trickle of current coming through here, so small that the voltage drop across here is just negligible. Now, the magnitude of this induced voltage, it doesn't depend upon the magnitude of the current. It depends upon the instantaneous rate of change of the current. So what happens is when we close the switch and instantly after that, the rate of change of that trickle of current through the coil is such that when you multiply it by the inductance value of the coil, that induced voltage will equal E, the battery voltage, and then it will decay off afterwards. Now the reason why it decays is this. The trickle of current, of course, gets larger and larger, so there's more and more current going through the coil, but the rate of change of the current becomes smaller and smaller. So, and we're going to show this explicitly in a few moments, the current through the coil looks something like this. So initially, it's the slope of this curve, you can see, gets flatter and flatter and flatter until it's just a horizontal line. So what it means is that initially we had a rate of change of the current large enough so that this induced voltage was equal to E instantaneously after the switch is closed, but then the rate of, even though the current through the coil is increasing, its rate of increase becomes smaller and smaller and smaller, so that this voltage drop becomes smaller and smaller and smaller, until finally there's just a steady amount of current going through the coil, no change at all, and of course that value is just going to be E divided by R. Here we are with just a steady amount of current going through the coil. It's just a horizontal line. And of course, the amount of that current is just going to be E divided by R. But initially, it doesn't change instantaneously from 0 to E over R. It goes through this curve, and the slope of that curve gets flatter and flatter and flatter. So as it does, the voltage becomes less and less and less, because as its slope gets smaller and smaller, that means that this is getting smaller and smaller, so this is getting smaller and smaller, until finally this is flat. Now its slope is 0. Now this is 0, so there is no more voltage, induced voltage, across the coil. That essentially is what we, some things that we discussed in the previous video. Now what we're going to do in this video is continue that discussion, only we're going to be a lot more analytical. So let's go across here. Now, when there's a current going through here, this has a voltage drop like this, because the current is in this direction, and the induced voltage across the coil, while it exists, has this polarity, so that it resists the current that's coming into there. That's Lenz's law. Now, if we sum the voltage drops across this circuit here, we will have I times R plus L di dt equals E. And this really is a differential equation. We want to solve this equation for the current I that's flowing through the coil. So it's not just a simple algebra equation, even though we have I here, but we have this derivative. So we have to solve this differential equation for I, and that's what we're going to do. And we need some room to do that with, so we're going to erase all of this, take this equation, write it at the top of the page, and then solve this differential equation for I, the current across that's flowing through the coil. So we had L times di dt plus I times R equals E. And we're going to solve this. So the first thing we can do, it might not seem obvious as a first step, but we're just simply going to take this over to this side of the equation. So we have L times di dt equals E minus I times R. Then multiply both sides by dt. So this is gone. And divide both sides by L. So I have di, make it a little bit neater, equals this. Now, we're going to divide both sides of the equation by this to get di divided by E minus I times R equals 1 over L times dt. And the reason for going through these manipulations is, of course, the way to solve the differential equation is that we're going to have to do some integrating. And here, this side would be easy to integrate, 1 over L dt. That's real simple. That's going to be 1 over L times t, plus an arbitrary constant of integration. But what about this side? Well, hopefully this is starting to look familiar, because if we have an integral of dk over k, that equals the natural log of k. And you can see we have di and I. These are both constants, but we're going to have to do some work with this integral before we can integrate it. And I think the first thing, let's just factor this r out of here. So for here, this is going to be the integral of di. Factor out the r, so we have r times E over r minus I. And that still equals this side. Now r is a constant, so we can take that to the outside of the integral. We're not going to put limits on these integrals. We'll deal with that later on. Well, this is a constant, so we can take it outside. It's in the denominator, so we'll have 1 over r take it out from here. Then let's multiply both sides of the equation by r. So here we'll have r over L. Here we'll have r over r, which is 1. So we now have this equation. And now this integral, we can fake it to make it look like this type of integral by doing a substitution. We say, let u equal this quantity, this constant, e over r, minus I. And then take the derivative of both sides, or just the differential of both sides. Try to keep things in better focus. Okay, so we have du. That's a constant, don't worry about that. So du equals minus di. Well, let's take the minus sign over to this side. Okay, so let's look at this integral. We had the integral of di. That's minus du. So I'll put a minus sign here, du. Then here it was divided by this stuff. But that stuff is what we called u. So we have this, and this is just equal to now minus the natural log of u. But what is u? That was our substitution for this. So let's write it in. So, and we have an arbitrary constant of integration. Call it that. Okay, so this integral equals this. And then this integral, that's real easy. That's just r over L times time times t plus another arbitrary constant of integration. So this integral equals this integral, which means then that this has to equal this. So let's write that at the top of the page. We're going to write that this equals this, and then continue from there. And actually, we're very close to our answer. There's just a few more steps that we have to go through, but let's go through them carefully so we don't get mixed up. But okay, first we're going to erase this. And we had minus the natural log of e over r minus I plus an arbitrary constant of integration, and that was equal to r over L multiplied by t, t is time of course, plus another arbitrary constant of integration. And we can bring this over here, subtract it from both sides. So this is gone. And this is just a constant minus a constant. So that's just going to be just another constant. So we'll call this just k prime prime. So take this away, write this in its place. Okay, now look what we have. That's just, I'm going to write a little bit bigger. This is the natural log of ER minus I. Minus the natural log of E over R minus I equals this. Now remember how it works with natural logs. If I have e to the natural log of x, of course that just equals x, that's just the property of natural logs. So I'm going to raise this side of the equation to e. So on this side I'm going to have E to the... Actually, before we do that, I want to do just one other thing. This negative sign, let's put it over on this side. So here, this will be minus, and this will be minus. That makes it easier to work with. Okay, now raise each side of the equation to the power E. So this, on this side, we're going to have E to the minus R over LT minus K triple prime. Just a bunch of arbitrary constants put together into one. Then here I'm going to have E raised to this power. Remember, E to the ln of x, that just equals x. So if I have E to this power, that's just going to give us this right here. E to the ln of x is x. So E raised to this power is just E over R minus I. I would have it a little bit neater. So we have E over R minus I equals this. Now we're getting very close. But look here, then we have this minus this. Here we can write this as E to the minus R over L times T times E to the minus K, like this, because multiplying these together is the same thing as adding the exponentials. So this, so let's look at it from here. We have these, you multiply these together. How do we do it? Well, we have one E, and then we just add the exponentials. So this and this are the same, but here we have E, this is a negative sign, but it's just a constant here. So this is just going to be another constant. So we can just call this thing constant K. So what we have is E over R minus I equals, we're just going to call this is just another constant now because E is a constant, raised to another negative constant. Doesn't matter, it's still just going to be some constant number. So we have K times E to the minus R over L times T. Now before we try to solve explicitly for I, let's see if we can figure out what this constant has to be. We know that at time t equals 0, I equals 0. We don't get that trickle of current to just immediately, just instantaneously after that switch is thrown, and we designate that as 0 plus. But at time t equals 0, I equals 0. So if t equals 0, I have e to the 0 power. That's just 1. E to the 0 equals 1. Any number raised to the 0 power is 1. So on this side, when t equals 0, this is 1, so I have k. I is 0, I have e over r. So we have determined then what this constant is. It's e over r. So let's write it in place of this. And again, we determined that just by using our initial conditions, that when t equals 0, then I equals 0. So take this k out and put e over r in its place. And now we're like one step away from getting our equation for I. Take I over here, and I will have plus I will equal e over r times 1 minus e to the minus r over L times t. And there then is our equation for the current that goes through the coil. And let's see, we've had kind of a long video. Why don't we just stop it at this point? Remember where we started off at? We had just a real simple setup, this, and then what we did was at time t equals 0, made this a complete circuit, and then what we have determined then is that the current that goes through the coil has this expression. So that's what we wanted to derive. We've done that. In the next video, we'll continue our discussion here. What we'll do is we'll think a little bit more what this looks like if we tried to graph it. And then remember what the voltage, the induced voltage drop across the coil is. That's equal to L di dt. So if I take the derivative of this, that will give us then the induced voltage across the coil at any time. So let's do that in the next video. We'll stop here. We derived the equation. That was our goal. Now in the next video, we'll think it through a little bit more exactly what this equation means, and from here, how we can also determine what the induced voltage is across the coil at any point in time.